In this video, we're going to continue talking about our MOS capacitor to get a better understanding of the field effect. So the second of our three operating modes is our depletion mode. And so in this case, we have a relatively small positive gate voltage, which is applied with respect to the substrate. So if we come down here to our diagram of our MOS capacitor, we're now going to put our battery with the positive terminal on the gate and the negative terminal on the substrate. And so let's say this is V1, and again, it's some small voltage. And it's important to note as well that we're still considering a P-type material. If we were considering an N-type material, we'd have to switch polarities and change our discussion a little bit. So what happens with this positive gate voltage? Well, we're going to have an accumulation of positive charges up here on our gate. And now remember, in our P-type semiconductor, we have an abundance of holes that are our free carriers, which of course have positive charge. So this positive charge on the gate, it can't travel through the oxide because we said there's not going to be any current there, but we can create an electric field. And so this is going to create some electric field in this direction, and that electric field is going to have the effect of pushing away any holes from this interface. So these holes here are going to experience a force pushing them down further into the semiconductor. And so when enough of those holes are pushed away, what's going to be left is just a layer of the exposed ionized acceptor impurities. And so remember, our acceptor impurities are going to be negatively charged. So we're going to have these negative charge acceptor impurities. And so remember, these are going to be fixed in our lattice. So unlike free electrons or free holes, these cannot move about our silicon lattice. So what we see then is we have this depletion layer. So sort of similar to what we talked about when we were looking at p-n junctions. And so this depletion layer is going to have some depletion width, which is specified usually by XD or WD. So this is our depletion layer with a depletion width XD. And so again, just to sort of put all of that into words, or at least the highlights, of course we have a positive gate charge. So positive gate, and that's going to push away our majority carrier holes. And then when we do that, we leave behind those fixed ionized acceptor impurities. So leave behind our charged acceptor impurities. And so we can make a note here that those are fixed in the lattice, so they cannot move. And ultimately what that creates then is a region where we don't have any mobile charge carriers, and we call that a depletion region. And hence the name depletion operation mode. So our third operation mode, we just sort of take that a step further, and instead of a small positive bias, now we're going to apply a larger positive voltage. And so the mode 3 is going to be called our inversion mode. And so again, we just have a larger positive bias applied to our gate. So larger positive voltage, and so I'm using voltage and bias kind of loosely, sort of interchanging, and that's fine. They both sort of mean the same thing here. So a larger positive voltage applied to our gate with respect to our substrate. Okay, and so let's go ahead and copy that MOS capacitor again. And so once again, we're going to put a battery still with our positive terminal on the gate, our negative terminal down there on the substrate. And so let's say this is some voltage V2, which is greater than our V1 that we had up here in the first part. So we're increasing that gate voltage. And so we still have this positive charge on our metal. We still push away those majority carrier holes. We still form that depletion region. So let's go ahead and draw all of that in. So we have some region here, which is depleted of our charge carriers. And so let me draw a few of these fixed So these are our fixed ionized acceptor impurities. So these are going to be throughout the depletion region. And so we still have some depletion width, XD, and of course we still have some electric field in this direction, E. And so what we're going to see though is as that V2, as that gate voltage gets larger and larger, we push away the holes, but at a certain point, that depletion width is going to reach a maximum value, and now we're actually going to start attracting minority carrier electrons from the p-type bulk. And so remember, because this is p-type, we have a majority of free carrier holes. In most cases, a whole lot more holes than there are electrons. However, there are still some free electrons in this material. And so these free electrons are going to move towards this interface as they're attracted by that positive potential applied to the gate. So what ends up happening is we end up creating an inversion layer of electrons right at this interface between our oxide and our semiconductor. So let's again sort of write down the key points there. So our depletion width reaches a maximum. So basically all the things we said in the previous mode happened, but now we say our depletion width reaches some max value, reaches max width, and then after this, additional gate charges are compensated by those free electrons in the p-type material. So additional gate charge is compensated by minority carrier electrons that are being pulled up to that interface. So our oxide semiconductor interface. So as I mentioned before, that layer of electrons we then call our inversion layer. And so what we can see is that inversion layer of electrons sort of allows us for a path, and what we're going to look at in the next video is sort of scaling this up, or not necessarily scaling up, but adding on some extra pieces to this. Let's say we have a reservoir of electrons over here and a reservoir of electrons over here. Well, now that we have this path in between, we have a conduction path for our electrons to transfer between those two reservoirs. So our inversion mode is what we're going to be operating in when our transistor is on and we have current flowing, whereas our accumulation mode, and to some extent our depletion mode, is going to correspond to our device being off and having no current or insignificant amount of current flowing.